Chapter 6. Tool Replacement. Step Drill. Next, we will explain the procedure for replacing the step-drilled form tool. First, we must verify that the length from the tool tip to the second step is consistent across this batch. If the tool lengths are inconsistent, it will cause unstable and varying chamfer depths during operation. Therefore, the first step is to ensure that the tip-to-step lengths for this batch of tools are identical. Once verified, we can remove the used tool. When removing the tool, be careful with the wrench. Do not rest the wrench against the fish scale chip guard. If you apply pressure, it will break. Remove the drill bit. We also need to remove this extension holder, because the shank diameter of our step drill form tool is 12 millimeters. This current holder cannot clamp a 12 millimeter shank, so it must be taken off as well. Collet also requires to be replaced. We need to replace it with a 512 mm collet. Now, retrieve the new step drilled form tool bit. It looks like this. As for the collet, install the collet as usual and insert the drill bit. When inserting the drill bit, ensure that the full shank is clamped inside if possible. If that is not possible, it must be clamped to at least 2/3 of its length. After inserting the step-drilled form tool, do not tighten the collet nut yet. Leave it loose so the drill bit retains the ability to slide up and down. Next, retrieve the gauge block. This is the length calibration block. The 138 millimeters marked on it means our reference setup value for later will be exactly 138. Mount the gauge block onto the tool's chamfered bevel like this, facing toward the second step. Once it is properly mounted, since the gauge block is marked with 138, we will move the spindle to the 138 position. The travel speed of the spindle for its advancement and retraction is controlled right here. Currently, the drilling feed rate is set to 5, so it moves slowly at only 5 millimeters per second. If you want it to move faster during manual mode, you can increase the speed up to the maximum of 10 millimeters per second. Then it will travel a bit faster. Remember to change it back to 5 before actual machining. The spindle cannot reach 138 right now, because the axis stroke travel is restricted by the limits here. Let's release the limit and increase the allowed range. It went a bit too far. All right, 138. Okay, perfect. Now, let's focus back on the drill bit. At this point, align this notch toward the coolant spray nozzle like this. Then push the gauge block forward. Push it forward. Hold the drill bit and push the gauge block forward until it firmly presses against the indexing fixture plate. Tighten the collet nut. Check the block. Now there is 0 clearance, which is perfect. This is our required reference coordinate. This is the tool length setup for the step drill. Every subsequent tool length calibration procedure will use this specific gauge block. The datum for a step drill is located on its second step. After finishing the setup, we will retract the spindle. We will lock it tightly with a wrench later. But let's retract the spindle first. Remove our gauge block. Once that's done, tighten the collet nut securely using the wrenches. After tightening it completely, we will place a workpiece into the fixture and rotate the indexing table over. Load a workpiece. Rotate it to the active drilling position on the table. The spindle needs to retract a little bit. No need to clamp it tight yet. We will advance the spindle manually. Stop advancing when you visually see it is almost touching the workpiece. Now, let's check the contact against the workpiece. There is still a slight clearance between the workpiece and the tool. Let's continue moving forward. Keep advancing. Watch carefully as it approaches. The remaining clearance is now about 0.3 to 0.4 millimeters. This position is perfect. No need to go any further forward. Once verified, check the coordinate. It shows 147.23. Therefore, we will define this current location as our contact position. We will use 147 as the contact position value. Next, let's retract the spindle. Retract it until our laser sensor path can align and detect the front tip of the drill. Let's verify this position. It looks about right. The coordinate is 123.59. Let's round it to a whole number, which is 124. So 124 will be set as our standby position. And 147 is configured as our contact position. Take a look at the screen. It is 147. Now, we need to configure the drilling depth parameter, since this is a two-step tool. The required drilling depth depends entirely on the length of this front section. So we must measure it. Let's check the drill bit. Measure it with the caliper. The distance from the drill shoulder to its second step is approximately 31.5 millimeters. Therefore, we do not need to add any extra over-travel depth. We just need to input exactly 31.5. So our total drilling depth parameter will be 31.5 millimeters. Okay, press enter. Next, the travel speed from point A to point B. Since traveling from A to B is a non-cutting stroke, meaning moving from standby to the contact position, this entire distance is a rapid approach non-cutting travel. We can set it to run at the maximum rapid speed of 100 millimeters per second. Now for the next section. The distance from B to C is our active cutting stroke. How fast should this cutting feed rate be? How many millimeters per second should it advance? Determine this by referencing the technical parameter datasheet provided by the tool manufacturer. Next is the deceleration feed speed before reaching the hole bottom, since the second step on this tool is designed for chamfering. This parameter does not need to be adjusted. It is typically only used for blind hole operations. Moving on, the retraction speed when returning from the bottom of the hole, C back to standby, A. Since the tool is retracting out of the hole, it is considered a non-cutting stroke. Therefore, we should set it to return at the fastest speed of 150 millimeters per second. Now, let's check our spindle rotation speed for this tool. The tool manufacturer's specifications recommend a spindle speed of approximately 2,200 revolutions per minute, since it won't directly display the value yet. How do we verify the 2,200 revolutions per minute? First, let's make sure there are no obstructions in front of the cutting tool, and that the tool is entirely safe to spin. Then we press spindle on. At this moment, the live spindle RPM will be displayed on the screen. The system utilizes this rotation speed sensor to detect the real-time speed of the spindle. For this tool, 2,200 revolutions per minute is required, but the current speed is too high, so we need to decrease it. Adjusting the motor frequency will change the rotation speed. It's still slightly above 2,200 revolutions per minute. So let's lower the parameter to 95 Hz. Down to 94. Down to 92. Down to 88. Alright, that is perfect. It is right around 88 Hz. Let's stop the spindle. At this point, our coordinates, reference positions, and all required parameters for this tool are completely adjusted. Now, we need to validate them. To run a verification cycle. Since we don't have any raw workpieces left to Euro, they are all finish 80 Euro. We will perform a dry run test for validation. First, we must close the machine safety doors. Both the front and rear doors must be closed, otherwise the machine cannot execute any movement. We will use auto mode. Combined with single cycle status, we will process one piece to validate each step consecutively. Turn on the coolant, and then hit auto start. If the machine does not start moving, we need to diagnose the cause. The notification indicates spindle not in safe position. Let's verify the current value. Clear the error code first. The screen shows 124.5, but our configured safe threshold position is 124. Since the current value is greater than 124, we must manually retract the spindle slightly. Retract it so that it drops below 124. Okay, perfect. Switch it back to auto mode and hit auto start again. Run a single piece. Stop and inspect the workpiece after each cycle. Once the single cycle inspection confirms everything is fine, let's check the next function. Because this tool is a step drilled form tool, the purpose of the second step is to chamfer. Earlier, we did not activate the parameter for the second step. So let's navigate back to the previous setup page. Right here, the secondary feed function must be toggled to on. Once enabled, we need to configure its specific feed rate. Because it is a chamfering cut, this feed speed cannot be too fast, otherwise the tool edge can easily chip or break. Therefore, we set this feed rate to run at 1.5 millimeters per second. Next, how deep do we want to chamfer? For this initial value, we can input an arbitrary placeholder like 1 millimeter or 1.5 millimeters. That will do. After entering the values, we execute the auto start sequence again, run one cycle, perform the chamfering cut once, and then inspect the piece. Collect the finished workpiece, verify it. Drilling quality is perfect, and the chamfer depth is correct. This matches our required specifications. Once inspection confirms everything is correct, if any parameter needs adjustment, we can modify it here. If the chamfer is too shallow, increase the value to 1.5 millimeters. If the chamfer turns out too deep, modify the parameter down to 1 millimeter. Adjust accordingly. Once everything is confirmed, we save the parameters to the memory registry. We recommend naming the profile based on the tool specifications. For this tool, shank diameter is 12 millimeters, drilling diameter is 6.8 millimeters, flute length is 30 millimeters, and point angle is 90 degrees. Input this specification description into the name field. Press Enter. Press and hold the first memory slot until it flashes on the screen. Then press Save to confirm. All our current parameters are now successfully recorded in this slot. This concludes the complete operation and calibration procedure for the step drill.